At the turn of this century, two powerful forces were preparing to clash: the British Navy and the German scientific community. Though neither was aware at the time, both would be involved in a life-and-death struggle for control of one of the most common elements on the face of the planet, nitrogen. For this simple molecule is the stuff of bread and bombs. To begin with, nitrogen is a basic food of plants. But although 4/5 of the air around us is free nitrogen, plants can't use it directly. Nitrogen must be fixed by chemically combining it to other elements, forming compounds which the plant can ingest from the soil. The nitrogen fixation process occurs continually in nature. Lightning forms compounds such as nitrogen dioxide, and bacteria in the roots of the pea family can produce the equivalent of 2.5 tons of fertilizer per hectare each season. Much of the precious fixed nitrogen, which feeds plants, is returned to the soil when they die. But Europe, at the beginning of the century, was robbing its soil of fixed nitrogen by intensive harvesting of food. So European countries replaced the fixed nitrogen by importing natural nitrate deposits. Chile supplied the world with 2/3 of this natural fertilizer, and Germany alone bought up 1/3 of Chile's production, both for agriculture and because fixed nitrogen is the key ingredient in explosives. In the unlikely event of war, the British Navy planned to blockade Germany, deny the Kaiser his source of explosives, and starve the German people into submission. But when war did come, the Allies had not counted on this genius, Fritz Haber, the most patriotic of Germans, who would invent the process for fixing nitrogen from thin air. Haber's challenge was to break the strong bond that holds nitrogen atoms together and combine them chemically with what? A nitrogen atom has 5 electrons in its outer shell. Of several candidates to combine with nitrogen and complete this shell, Haber decided that 3 hydrogen atoms were the most promising, forming ammonia. By working with the chemical equation for the formation of ammonia, and of course by watching Program 4 in this series, Haber knew that the removal of heat should favor the production of ammonia. But in reality, Haber was unable to detect the formation of even a trace of ammonia. This indicated that either the rate of the forward reaction was extremely slow, or Le Chatelier was wrong. Haber also knew that 4 volumes becomes 2 volumes in this forward reaction, which tends to decrease pressure in the container. He encouraged this reaction by applying more pressure to the system to squeeze out ammonia. Foiled again, even under hundreds of atmospheres of pressure and low temperatures, he was unable to produce a whiff of ammonia. Neither Haber nor Germany could wait for such a slow reaction. Haber realized that adding heat speeds up all reactions. If no product is around to interfere, the reaction would run in one direction. The presence of the product ammonia was certainly not the problem at first, so a high temperature could be used to produce ammonia. Haber's enemy was the ammonia itself. As it increased in quantity, the heat began to favor the reverse reaction back into nitrogen and hydrogen until finally an equilibrium was reached with only a small amount of ammonia present. If only a small yield of ammonia was possible, Haber decided to achieve it quickly. He found that uranium and osmium, of all the catalysts he tested, produced the greatest increase in the rate of the reaction. From his data, Haber was able to calculate that a compromise could be reached between the rate of the reaction and the concentration of the product in the mixture of gases. At a pressure of 200 atmospheres and a temperature of 600 degrees Celsius, he produced 100 cubic centimeters of ammonia, barely an 8% yield. But the rate of the reaction made the process commercially feasible. In the Haber process, pure nitrogen and hydrogen gas are pumped into a pressure vessel containing a catalyst. Pressure is applied and temperature is raised. The stress on the system is an enormous excess of nitrogen and hydrogen molecules. And as Le Chatelier predicts, the reaction shifts to produce more ammonia molecules, speeded by heat and catalysts. The mixture is continuously drawn off before it reaches equilibrium, which reduces the potential yield, but delivers a steady stream of gas to a cooling tower, where ammonia is liquefied and separated. The hydrogen and nitrogen, which remain gaseous, are continuously recycled to maintain a steady state. Hydrogen and nitrogen in, hydrogen, nitrogen, and ammonia out. The net effect is a removal of ammonia molecules, a stress which, as Le Chatelier predicts, is counteracted by a steady reaction to produce more ammonia. The rest was up to German industry. In 1913, their factories produced 7,000 tons of ammonia. By the end of the war, 200,000 tons. So much for the blockade by the British Navy. Haber single-handedly prolonged Germany's war effort by a few years. As a true German patriot, he put his lab to other uses. At the request of the War Ministry, he developed and personally supervised the use of chlorine and mustard gas, which nearly routed the Allied armies. In 1919, he was awarded the Nobel Prize for his ammonia process and was the only recipient in its history to have the honor contested. Allied scientists were slow to forget the damage he had done during the war. But the greatest insult of all came from his homeland. Haber was hounded from his beloved country for the crime of being Jewish. Distraught, he wandered Europe and died broken-hearted a few kilometers from his beloved Germany. Perhaps history seeks an equilibrium as well. Hundreds of millions now depend for their well-being on agriculture fertilized by the Haber process. Today, Haber is recognized for his mastery of chemical equilibrium and has been restored to his rightful place in the pantheon of science.